Okay, so this is a small lecture. We'll cover one part of uh, contour integrals. Just to demonstrate as an example, when are these integrals? Uh, how does one parameterize and do these integrals? So let's say I have a point A, point B, and I have some path C, and I want to evaluate FCDZ. We parameterize in terms of some variable. We can parameterize the path in terms of some variable. So let's say that variable is t between the range alpha and beta, and xt and yt are the real and imaginary parts of z. So what does a become? The point A over here, that becomes x alpha, y alpha, real and imaginary parts. And similarly, B becomes x beta, y beta. And in general, fc dz over the integral, we can write in terms of the way we have parameterized it. So I have fc dz over the contour or over the path C. That is nothing but dz becomes dx plus iota dy, and similarly I have u plus iota v. That was my f over here. So what do I have? This breaks into four integrals: u dx minus v dy plus iota u dy plus iota v dx, and that becomes u dx by dt minus v dy by dt times dt. Just expressing this as an integral over dt. U so as long as dx by dt and dy by dt are continuous, along the path C, we can evaluate this integral. So for example, let's take a particular example. Fz equals to 1 over z, and integrate this let's say t is the parameter, which is the angle, and let's say the contour is the whole entire circle closing it. That's your contour. So I can write the path which the zt takes, or parameterizing any point zt, is nothing but r cosine t plus iota r sine t, and dz by z, the integral goes now from 0 to 2 pi, because t goes from 0 to 2 pi, dt d 1 over z. So what do I have? I have this integral becomes nothing but 0 to 2 pi. I take dt on this side. dz by dt from this expression is nothing but minus r sine t plus iota r cosine t divided by r cosine t plus iota r sine t, which becomes 0 to 2 pi dt times I is equals to 2 pi iota. So the contour becomes, the value is the answer. You can see the answer is independent of R. We'll also consider a case, let's just consider a case where we have a contour which depends upon the path. Well, in the sense that it depends upon which direction we take the path. So, for example, let's say I have this guy R. I'm considering a semicircle path from plus R to minus R of the same function, and let me call this curve as C2 dz by z from plus R to minus R. As you can see from the above formula, this is nothing but going from 0 to pi over here. So the answer is going to be iota pi. Similarly, I can have traversing it the other way, C3 dz by z minus R to R, and that is from pi to 0, and that's going to give me minus iota pi. And if I add these two paths, C2 plus C3, evaluate the contour integration over some of these guys, dz by z, and that is going to be equals to 0, which is not equals to 2 pi iota. So you see, I can have C2 plus C3, or I can have the whole integration over the whole contour. The answer depends upon whether or not I enclose the origin. Enclosing the origin, where this function had a singularity, affects integration. So in the next lecture, we are going to see Cauchy's residue theorem and a shortcut ways to do contour integrations. Thank you.